Welcome back to our Chapter 10 notes over solubility product equilibrium, KSP. This will be our final video. We are finishing off our notes with this question, and you'll notice it at first looks just like the one we just did. A beaker has a mixture of these three ions. We're going to add some silver. We're going to precipitate the ions, but check out the change in the question. Now I'm being asked to calculate the percent of the iodide and bromide ions that have precipitated right before the chlorine starts precipitating. So in other words, when I have added enough silver to precipitate the iodide as silver iodide and the bromine as silver bromide, what percentage of that can I filter out before the chlorine starts precipitating? Because of course, if I start precipitating the silver chloride, then I get a mix of all three precipitates and all three would sit in the filter, and maybe I don't want that. Maybe I want all three separate. So it's a good thing to be able to calculate is, what percentage you would have before the other starts. I know it sounds super complex. It really is not. Percentages are one of the easiest things that we do in AP Chemistry because it's just a part over whole. Here's where we need to start thinking. What is the part that I'm looking for? What would be the whole amount that I'm looking for? We are given the whole amounts. We will need to calculate the parts. What parts are precipitated out when the Cl starts precipitating. So the biggest hurdle in a question like this, and I would find it unlikely that this would be a free response question because this would be a lot of time consuming calculation that really doesn't show you know a lot of chemistry. It is cool chemistry, it's useful chemistry because this would be something we would need to know. How great is your lab results before you do something? But it's going to be a lot of calculations and a lot of calculator time. So not likely to be on the test in the free response where you have to calculate it out. Could be modified in the multiple choice. And this would be a great culmination of everything we've been discussing. So our first hurdle is, where do we start? Well, we want to start where the Cl starts precipitating. So how am I going to know where the Cl starts precipitating? Well, the Cl is going to start precipitating when let me switch to a brighter color, when my AgCl, which is in equilibrium with silver ion and chloride ion, when that starts forming a solid, it is equal to the KSP. These concentrations multiplied together, raised to their coefficients, will equal KSP when it starts precipitating. So that's my when, and that's the power of KSP, is it can tell you when. So let's start there and switch to a darker color. So again, when AgCl, which is in equilibrium with Ag ion and Cl ion, when the KSP for that is equal to the concentration of silver ion raised to the exponent of the coefficient. The coefficient is the exponent. And I point that out because students miss that quite often. Be very, very careful, especially since we're not practicing with anything that has coefficients. Just be careful in your practice work in class. When this is a true statement, when this equals that, the AgCl will start forming a solid. What I want to know is, how much silver will that be? Well, the good news is we know all of the other variables. We know our Cl minus is 0.0010 molarity because that's given in the problem. We know our KSP, that's given in the problem, 1.8 times 10 to the negative 10. So X, which is the concentration of silver ion when, concentration of silver ion when it starts precipitating, is equal to 1.8 times 10 to the negative 7 molarity. That's how much silver will be in my beaker the moment that AgCl starts to form a solid. Now, we obviously should be slightly under that if we don't want to precipitate the AgCl solid, but you can imagine with a number this small, it's a close enough approximation for our work that we're going to just go with this number. So check out what I'm going to do. I'm going to take them one at a time. So let's do, it's just next in the list, AgBr. Okay. So switching colors to keep it all separate. Let's go with dark red. With AgBr, I'm looking at this equilibrium. And I'm looking at this KSP. And again, I point out coefficients are exponents, exponents are coefficients. And we do not include solids. These are solids. We do not include solids and liquids in our KSP expressions. And I proved to you earlier that why. So if you need to review that, it is because their concentrations really do not change an appreciable amount. So we don't include them. So just be aware of that. With that said, so here's our KSP expression. Now I do know a KSP. So I know that 3.3 times 10 to the negative 13 is equal to, I don't know why it keeps switching that way. I know that is going to be equal to, check out what I know. I'm going to use this value. This is different than before. I'm going to use this value for my concentration of silver, and it's the concentration of bromine that I'm going to be able to solve for. So it's, yay, fun, calculator time, hooray! Lots of fun with the calculator. I know you feel my joy. And yes, that's all sarcasm because, honestly, you're not going to have much calculator time on the test. It just is not that kind of test anymore. You will need to use your calculator a little bit, not a significant amount. So when I divide X, and again, we want to say what X is. X, which is bromide ion, is equal to, I'm going to go in scientific notation, 0.20 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 10 to the negative 6 molarity. Okay, now let's interpret this, because that's a number we need to work with, but let's interpret what that is. That is the concentration of bromide ion that will precipitate with this amount of silver and still be ion. Okay, did you catch that? I've solved for this portion. That's how much is still ion. That's how much is left after I've formed the solid. I've put in how much silver I have available, which is way more than I would need to start this reaction. We discussed that in an earlier video. I am forming solid. This number here represents how much ion I have left. Okay, now let's go back to the original question. The original question is calculate the percent of it precipitated. Did I now have a number for how much precipitated? Please tell me no. I do not have a number for how much precipitated. I have a number for how much is left as ion. So how do I know how much is precipitated? Well, that should be an easy question in your head. Take your starting amount, subtract what is left over, and that will get you how much has precipitated. So, how much has precipitated is 9.98 times 10 to the 1, 2, 3, 4, 10 to the negative 4 molarity. Okay? Now that's my part. That's my part that has precipitated. I wanted a percentage. So part over whole, 0.0010 molarity is what I started with. Show the times 100. The AP people say they need to see that. I'm not sure why, but they say they need to see that. So be sure you show that. Okay. So now I'm going to take that and I'm going to divide it by the 0.001. And I'm going to multiply that by 100. And check out my percentage. And I'm going to use a lot of decimals to overkill. This is too many significant digits, but it's going to show you, it's going to give you indication of, the results. Check this out. 99.8167, so 99.8, almost 100% of the bromide ion has precipitated out by the time I start precipitating the chloride. And that's what we would expect with a difference of 1,000 between these, which makes this a good technique for removing and separating these. What if the difference was, say, 10 and not 1,000? I would certainly not be close to 100. I would have only a little bit precipitated out by the time the other started. We would do the calculation exactly the same. It simply would give us a much lower percentage has precipitated. Okay, now I'm going to ask you a theoretical question, and then we're going to prove it with calculation. If by the time this precipitates, I have 99.8% of this precipitating, should I have more or less of this precipitated out? Now notice if the KSP is smaller, that means it's going to want to precipitate more. It's going to be more likely to form a solid. So in theory, and we will check this with a calculation, in theory, I should have an even greater amount precipitated of the iodide when I start precipitating the chlorine. Okay, so we're going to now do the same calculation we just did, but we're going to do it for iodide. So I'm going to start by erasing this bottom half. You have the luxury of going to more paper if you need more room. I am stuck with one screen, so I certainly would not erase on the test. I am just erasing to fit it on my screen here on my tablet. I don't know why my eraser started missing all these little bits. There we go. Okay. And let's go with dark green. I'm going to focus on the silver iodide. So my formula, AgI in equilibrium with Ag ions and ions. My KSP, and the coefficients are the exponents. And I don't write solids and liquids. And now I have my, let's fill in what we know. My KSP for silver iodide is 1.5 times 10 to the negative 16. My silver ion concentration is the same as we first calculated, 1.8 times 10 to the negative 7 molarity. Now I'm looking again for the I in this equation. So we have fun with our calculators yet again. We're going to take our KSP and we're going to divide by the silver ion concentration we first calculated. Same silver ion concentration because I'm working in the same beaker. And X, which is concentration of iodine left over, is 8.3 times 10 to the negative 10 molarity. Now I need to find my percentage, but I need to know the percentage of what precipitated, not what is left over. So 0.0010 molarity minus the leftovers of 8.3 times 10 to the minus 6 molarity. Oh, sorry. There we go. Okay, give you a chance to copy that down. 0.001 minus our 8.3 times 10 to the negative 10. If my calculator would behave. And you know what? Oh, I'm back to red. Weird. My calculator wants to tell me that I have precipitated that much. Well, what do you notice when we do part over whole? You notice that it is 100%. Is this truly 100%? I mean, let's use some common sense here. Is this truly we've precipitated 100%? Well, no, because that minus that is so not that. But where's the difference going to be? Okay, the difference is going to be, it's going to be 0.000999992. If I had enough nines in there. I think I do. When you round all that to significant digits, I mean, we easily get back here. So we can, within significant digits, claim that 100% of our silver iodide is precipitated out as the silver chloride begins to precipitate. To calculate this to any more significant digits, sure, you could do it. It'd be like, 99.999992 or something like that. Again, two significant digits, we have 100%. Now, I told you earlier, based on the value difference here, and it's 1,000 times difference, we would expect this one to have been higher. We would expect more to have precipitated out. And we see that. So go back to the silver bromide example. Check out that percentage. It wasn't exactly 100. And then look at this one, and it is 100. For our purposes, it is easily 100% has precipitated. So it is a higher amount. Why is it a higher amount? It has a lower KSP, which means less ions exist in equilibrium. Much more solids going to exist. Okay, so I hope you see by now, I mean, really the point of this was how we can predict the percentages and what order that would be in. How we start the problem, because I'm betting half of you probably would have difficulty just getting started. Once you got started, it kind of went pretty easy from there. Are the calculations bad? No, they're not difficult. We didn't need a quadratic or anything. Are they going to be time consuming to do something like this? Well, yes. So you certainly could practice this in class, and it could be on the test. I'm just going to say, and this is the last I'm going to say about it, the big calculation examples like these probably are not likely to be on the test. Because again, yeah, this does chemistry, but this proves you can do math with the chemistry, not that you understand the chemistry. And the test is focused much more on, do you understand chemistry? Do you understand what a KSP is? It would not shock me if they were to give you these numbers and ask, what order will they precipitate in? And if this one is starting to precipitate, what would your estimate be of the amount of this that has already been precipitated? And you can see this is 1,000, that's 1,000. So with 1,000,000 times difference from there to here, you can see it's easy enough to assume it's 100%. Because that is certainly a very two significant digit valid assumption. So good luck on your practice on this, and we are ready to move on to another type of equilibrium.